Welcome learners. In today's lecture, we are going to continue our discussion on potential gradient, and then we are going to solve few problems associated with this topic of potential gradient. So let us see a brief intro of what potential gradient is and what is meant by gradient. So the literal meaning of gradient is that something is changing. So gradient means something changes. In our scenario, the potential represented as V is changing. So we want to know that if we are moving from point A to point B, or any charge is moving from point A to point B inside the electric field, how much is the change in the potential, which we identify as the potential gradient. So before we begin our discussion on potential gradient, another thing that we have to remember is there were two ways or two mathematical expressions which help us in finding the potential V. The first one is shown over here, that is associated with distributed charges or system of charges, but since this is an integral, so we can also utilize it for continuous system of charges, where this potential is also represented as a volume charge distribution of rho v inside any field R dV divided by 4 pi epsilon and then the distance between those charges. So we say that this is for the continuous charge distribution, and the above one is utilized for system of charges where we have more than one charges like Q1, Q2, Q3, as we have seen in our previous explanations. But the thing to note over here is that although these two equations, equation 1 and equation 2, are valid in finding the potential for any source charge, the problem arises that most of the time there are unknowns in finding the potential, which means that sometimes electric field intensity is not provided to us, sometimes the potential or the charge distributions, whether it is volume charge, line charge or surface charge, is not given to us, and most of the time we mostly forget about the representative equations for the differential elements, that can be differential length, differential volume or differential distance. So we should have another way that is more easy and friendly mathematically, which can help us find these unknowns, for example the electric field, and then it is also going to be helpful in finding the potential. So this means that in today's lecture we need to figure out what can that new expression be other than understanding the potential gradient. So we want to find a relationship where we can find the electric field intensity when we have been given the potential V. In the above two equations, equation 1 and 2, these are used to find the unknown potential, which is V, but we want to find another way, or a third equation. Let us put it this way. We need to find a third equation that shows the relationship between E, which is the electric field intensity, and the potential V. So let us see if we can find that expression or not. So in order to begin our discussion, we are going to use this figure provided to us, which is basically representing the flow of electric field from your left towards your right, which we are going to say difference between potentials, and then we can select any point or a charge that can move inside this field. So let us dig into this and see what is the relationship we can find. So basically we need to find or understand a new method that helps us in finding the electric field intensity E from the potential V. So this is what we want to do. So we need to find a third expression that shows the relationship between E and V. In order to do so, let us take the analysis of this image that is shown over here. So let us consider that this is the electric field. Let me call this as E, and it is moving from a source of unknown kind, so we don't care what the source nature be. It can be a single charge or a line of charge, but we know that there is a high potential on this side and it moves towards a lower potential. So this is where our source is, and this may be the location where we want to find the potential or the electric field intensity at that point. So this is the scenario that we have, and all these red lines are the electric field lines. So now let us see what we can do with these electric field lines. Let us say we draw the equipotential surfaces for these electric field lines. So we know that equipotential surface is such that these lines are always normal to the electric field, and the potential on these lines is the same, or the potential difference is zero. Let us say the first equipotential surface is at 50 volts, the second is at 40 volts, this is at 30, 20, 10, and the last one, or the lowest potential, is at 5 volts. So for this equipotential surface, any point if we select, let's say this is point A and this is point B, the potential difference between these 2 points, let's say delta V, will always be 0 volts, or we say that A and B have the same potential. Thus it describes the equipotential surface, and we can see that it is only having a single voltage, that can be 50 volts for the first one, 40 for the second, 30 for the rest, and the last one is having the lowest potential of plus 5 volts. So now let us take a point inside this electric field and see how can we begin our analysis. I can take any point in this electric field. Let's say I start from this point where my charge Q is, and I take a very small final point that is moving from one equipotential surface of 20 volts to other at 10 volts. So I can say that the charge plus Q has covered a distance, or a very small distance, of delta L along AL. Similarly, I can take one point over here for the charge and I can move it to this direction. Again, this is a charge Q. The distance it is covering is delta L, and the unit vector is along A of L. This distance delta L can move along the electric field, it can move opposite to the electric field, or it can be perpendicular along the equipotential surface. So these are the three distances or small distances we can cover, and each respective distance will have its own unit vector as AL. So this is what we already know from our previous chapters, that what is a unit vector along a certain distance. Now let us derive the value of this electric field for charge Q based on the potential differences between 2 points, let's say the initial point over here and the final point over here. So let us see how mathematically we can develop a relationship between E and V. So we can say that if we have the line integral relationship between voltage, the potential and electric field, which we call as absolute potential, we say that it is V equals to minus E. We have an initial point to the final point, and then we have vector E with a dot product of the small distance that we have taken. If we are just taking a smaller distance, as we have seen over here, that we have just taken delta L for charge Q to move from the initial point to the final point, we can represent the integral in the form of its differential, or the differential elements. So I can write it as delta V is equal to minus E dot delta L. Since this is a dot product, I can write it as minus E delta L with the relation of cos theta. So we can change this del operator into a differential operator, or a direct differential like dV, and I can bring this L in the denominator, so it will be minus E cos of theta. Now we know that delta L is making a certain angle with this theta. For instance, this is the point where the angle is being made. If we talk about the dot product, which is the projection of one vector onto the other, in this case we are having a projection of this vector onto delta L over here. So if I take the maximum of cos theta, let's say if I take cos theta equals to -1, the maximum bounds of cos theta, and input it in this equation, then dV by dL is going to have a value of E, and I say that this is the maximum value of the electric field, and this is the first expression which we are getting. So why this is maximum? Because if we have taken delta theta over here, or cos theta, we know it is 0, 90, and then the maximum will fall at minus 1 or 180 degree. So this is the maximum length that we can take, and if we move in the opposite direction of delta L against the electric field, which means that if this is the point and the electric field is moving from higher potential to lower potential, then if we take delta L, or the small distance, in the opposite direction of delta E, this is the 180 degree that we are taking for this cause. So this is where we get the maximum effect of electric field. Thus we can summarize equation 1 into 2 points. We can say that the observation from equation 1 is that the magnitude of electric field of E is basically given by the maximum rate or maximum value of a rate of change of voltage, or rate of change of potential V. So this is the potential V with the distance, or with the incremental distance, let's put it, because it's delta L. So it is incremental distance. So if you want to find the magnitude of V, it means we have to take the rate of change of potential in the maximum direction, which is opposite to E, as we have seen over here. This is the opposite of it. And second observation we can take from the same equation is that the maximum value is obtained. The maximum value is obtained when the direction of incremental distance delta L is opposite to the electric field intensity E. So these are the two observations which this equation 1 is given, and that is helpful to us whenever we are solving numericals related to such equations, or showing the relationship between E and the potential V. So now, since we have written this first equation, we still want to make sure that whether other possibilities exist or not. So can we find a better relationship than what we had as equation 1? So let us say if we want to establish even a stronger relationship, let's say we want to establish a subtle relationship, or we want to go a step further and have a concrete equation between electric field and potential. So let us again go back to our image, and this time we represent the image in the form of equipotential surfaces being our focus point. So let us take another scenario where now we have equipotential surfaces as such. So let's say this is the first equipotential with a certain voltage, this is the second one, this is the third one, and then we have something like this. So we can say that the first equipotential voltage is, let's say, at 90 volts, the second is at 80 volts, and then we reach to 5 volts, something like this. So these are now the equipotential surfaces. This is another way to represent the equipotential surfaces. Now if you want to create the electric field against these equipotential surfaces, we know it is always appearing as normal to the equipotential surface. So we can assume that the electric field is in this direction for most of the cases. So this is the electric field shown over here. So now in this scenario, our electric field is again moving from a higher potential. As you can see, it is moving from 90 volts to a lower potential towards plus 5 volts. Now in this scenario, we introduce another element, and we want that element to be represented as A of n, which is moving in the opposite direction to the electric field. So now this is the scenario that we have, and now we want to take any point, arbitrary point in this electric field. Let's say I take this point P, and I want to now figure out that the two observations we have taken for equation 1, are they applicable to point P in figuring out where is the direction of the electric field and where is the maximum potential. So let us see if we can consider point P as our starting point and find these characteristics as shown as point A, and let me call this as point B. So if we are at point P and we want to see where is the maximum potential, or at which point the maximum potential is increasing, we see that if we move against the electric field, so in this way the maximum potential will vary across this small length. So we are going to have a maximum value of potential if we move against the electric field. And if we want to find the electric field, so we know that its movement is opposite or always opposite to the smaller incremental length L. So if we move from point B towards the right, as we can see that electric field is moving towards the right, so this is the point where the maximum E is going to be. So we have recreated this first scenario, this scenario from the first scenario, and we applied the two observations shown here in A and B to this point P inside the electric field, and it is giving us the same behavior as we saw over here, where electric field is always opposite to the incremental length, and that incremental length shows us that this is the maximum change in potential inside this field. So once we have this scenario, let us see what is the equation of the electric field for this scenario over here. So again, we know that potential is related to electric field as E dot d of L, and if we are taking incremental potential, so it is minus E delta L. Now if we had taken delta L to be perpendicular over here, which we can because the potential can be maximum perpendicular to point P or electric field, but in this case we know that it would also be equal to 0 because it will make an angle of cos of 90 for the scalar product. So this means that E and delta L cannot be perpendicular. So this is another observation that we see, that E and L cannot be taken as perpendicular because this will result in the potential being 0, and this is not what we want. We want the potential to exist. This means that the only possible way where the potential can exist, if we stick to our equation such that delta V is equal to minus E delta N, and we take cos of certain value, let's say -1, or we can take cos theta to be 0 if the projection is successfully happening, if this is the condition. So in the previous case we took cos theta to be -1, now we want the angle to be the same or they are in parallel. This means that in this case electric field comes out to be minus, so I'm changing the del operator to dl, and this is the maximum that we are getting. And now we introduce another element that is in the form of A of n. So this is now a new expression for the second scenario, that is relating electric field to the potential, where we have taken electric field moving from left towards right, that is from higher potential to a lower potential, and the del L is now represented as A of n, which is a unit normal vector which is in the opposite direction to the electric field moving from the lower potential to higher potential. And this is now another expression that we can take. So let me call this as equation number 2. So now we have two equations of electric field based on two different scenarios. Equation 1, when we get the maximum electric field if the cos angle is 180 degree, and the second equation of the electric field when the angle is the same or the projection is parallel. Again, if we look at second equation, we know that the negative sign is saying that the electric field exists if the direction is opposite to it. So if this is the electric field, this is the delta L, which is now being replaced as the normal vector, and this is the perpendicular where we don't want to go because this will result potential being 0. So now we move on to another step, keeping in mind that for equation 2 delta L is now replaced with the normal vector A of n. Now we want to introduce another element into the equation where we say that the rate of change of voltage can also be written in terms of n such that it corresponds to A of n. This means that equation 4 or equation 2 can be written as minus dV by dn along the A normal vector. So this is another way of representing where we basically changed L into any distance that is n. So let us call this equation number 3. So now we introduce another term into the mix so that we can get the value or the relationship between E and the potential. We say that if we ever take gradient of any value, let's say if I take gradient of t, it can be written as grad of t, which is basically the differential of t along n, which along the normal vector. So this is something that we have now introduced in our proof. So this is what the gradient is. Again, it means that the value of t is changing with respect to any distance in the direction of an, which is a unit vector normal. So I can say that my equation 3 with regards to this comes out to be, I can write equation 3 as E is equal to, so I can say that dv by dn is similar to dt by dn. So I can say the equation 3 of E can be written as minus gradient of v. So this is what I have done. I call this equation number 4. So now this is the equation which I am having, where the electric field equation is now represented as a gradient of some value, and that in this case is gradient of v. So now let us see how can we represent equation 4 in better terms, or how can we represent it mathematically such that our finalized equation is received. So this is our main equation, or the new relationship that we have found between E and V. Now what is V, or what is a better way to write V? So I can say that V is basically a function that can vary with respect to coordinate systems. It means that if we have any electric field over here, then the V potential can exist at this point, it can be over here, it can be anywhere. So this is what this is, as it's a function of any coordinate system. So which means that this V can be represented as a small or incremental change, and if it is a function of multivariable x's, then it is represented as a partial differentiation. So V can be written as partial V by partial of along x d of x plus partial V partial y along d of y plus partial V partial z of d of z. So this is how we can write the equation. Similarly, we also note that the small voltage in our case is also written as the relationship between electric field and dl, the small distance, where we know that E is basically the scalar component along a of x plus a scalar component along a of y plus a scalar component along a of z, and if we multiply it with d of L, so d of L, so this is the representation of electric field, and d of L, if it is a rectangular coordinate system, is d of x along a of x plus d of y along a of y plus d of z along a of z. So if I take the dot product of these two equations, and let me utilize this space, so if I take the dot product of these two terms for dv, so this dv then comes out to be minus e of x along d of x minus e of y along d of y minus e of z along d of z. So now if I compare both dv equations, let's say I call this equation A and I call this equation B, and now if I compare A and B just to see how the dv can be represented, so I can immediately say that the value of e of x from this equation comes out to be negative partial derivative of v along x. Then I can say e of y comes out to be negative partial derivative of v along y, and e of z comes out to be negative partial derivative along z. Thus I can write a combined E field equation as minus partial derivative of v along x, and let me call this a of x, plus partial derivative of v along y, a of y, plus partial derivative of g along a of z. So this is the expression of electric field which I am getting when comparing both the differential potentials, that is dV. So this is the value of electric field which I am getting. Now once I have this value, what else can I do with it? Because I want to represent my third relationship in a more technical way. So what I can do is that I can take my same equation of E which I have written. So let me rewrite it over here. E comes out to be negative partial derivative of V along X, this is for A of X, plus partial V along A of Y plus partial V of Z along A of Z. So what I can do is I can see at the equation and I can compare this. So let me call this as equation number 5. Now what we want to do is we want to compare equation 5 and with equation 4 and see how can we represent equation 4 in terms of E. So if I compare equation 4 and equation 5, so I know that equation 4 is, so I'm going to write equation 4 is minus gradient of V, and equation number 5 is over here. So if I compare this, I can say, or let us look into equation number 5. So equation number 5, there is something that we can extract from equation number 5, and that is this thing. So if we focus on the partial of x along A of X excluding the potential V, if we focus on partial of y along A of Y, we focus on partial of V along A of Z. So we know that this is nothing but a del operator. Del operator is partial by partial x along A of X plus partial by partial y along A of Y plus partial by partial z along A of Z. So this is a del operator. So I can replace equation 5 as E equals to negative. All these terms are replaced as del and the remaining value is V. So I can say that equation number 4, which was this one, is now represented more technically as this part, where the electric field intensity can be figured out if I take the negative gradient of any potential. In this case the potential is V. So this is the equation which we found, or the third relationship where we can find the electric field intensity from the given potential, keeping in mind that this is a vector quantity, this is a vector, and then we have a scalar element over here. So this is the equation which we can use to find the electric field intensity if we know the potential. So some of the conversions that are useful whenever we are talking about gradients, or especially the gradient of V over here. So if the gradient of V is to be found for the Cartesian system, we can use this equation. If it is to be found for cylindrical, we have to use this, and for the spherical, this is the condition that we can use. Now let us look at a problem and see how can we apply the gradients and the electric fields and the potentials. So in this question we have been given that you have a potential field in the cylindrical coordinate system. So again it means that if we are dealing with del of V in finding electric field intensity, this is the value of the gradient of V that we have to use for the cylindrical system. So the coordinates are value of V. So let us start the solution for the first part. So the value given is that potential is equal to 100 divided by z square plus 1 rho cos of 5 volts, and we have been given the values of the Cartesian coordinate systems, where Cartesian coordinate systems are rho, phi and z. So it is 3, 60 and 2 at point P. So we need to find the values at P. For the first part, what is the potential at P? For the second part, what is the electric field intensity at P? So the third part is what is the magnitude of E. So whenever you see an italic E, it means it's a magnitude. So let me write it over here. It's a magnitude. And the bold one is basically the electric field intensity. Then in part D, we need to find the ratio of dV by dN, what is the direction of the normal vector, and what is the volume charge density in free space. So in the first part, we need to find what is potential at point P. So let me call this as potential at point P. So in order to do this, we know that the values at point P are, or we know what are the values of rho, phi and z. So we just incorporate the values of rho, phi and z into V of P. So V of P comes out to be 100 divided by z is 2 square plus 1, rho is 3, cos of phi is 60 degree. So once you solve this, you get the value of 30 volts. So this is the potential at point P for the cylindrical coordinate system, and this is what we are getting as an answer as well. So now let's come to the second part. In the second part, we need to find, so let me use this space. So let us now do the second part. In the second part, we need to find what is electric field intensity. So we know that electric field intensity is negative gradient of potential, and this potential has to be at point P, so we write it at P. So electric field intensity at point P. So in order to do this, let us first figure out what is del V over here, or the gradient of E. Since this is cylindrical coordinate system, so our value of del V will be this one. So let me write it over here. So let us call this as equation 1, because this is what we want to eventually get at the end, where the gradient of V comes out to be for the cylindrical coordinate systems at rho V by rho phi along a rho, then 1 by rho partial derivative of V along phi a phi, and then you have partial of V along Z along AZ. So let us find these one by one. We start first with this part, then this part, and then partial derivative of the last. So we take partial derivative of V along rho A of rho. This means we have the value of, so what is V? V is basically this portion. So let us take the partial derivative of this along rho. So the value will be partial derivative of V, that comes out to be 100 rho cos of phi divided by z square plus 1. So let us do the partial derivative of this. So since we are just taking the derivative with respect to rho, so I can bring out the coefficients, and we will be left with 100 and cos of phi divided by z square plus 1, and you take the partial derivative of rho, so it is basically 1. So this means this is your answer. So 100 cos phi z square plus 1. Similarly, let us find the partial derivative of V for the second term. So now for the second term, we find the partial derivative of V, or let me look at the equation. It is 1 by rho. So it comes out to be, for the second part, 1 by rho partial derivative of V with respect to phi, it is equal to 1 by rho partial derivative of V. So let me write the value of V. It is 100 rho cos of phi divided by z square plus 1. So now if we proceed with this, we will have a value of, so the rho and rho will cancel out, and we just need to take the differential of cos of phi. So I can write it as 100 divided by z square plus 1. I can take this out, and I'll be left with, you take the partial derivative of phi of cos of phi only. So this comes out to be 100 divided by z square plus 1, and the differentiation of cos is minus sine of phi. So this is what you are getting for the second one. Now let's come to the third part of finding rho with respect to z. So then we take, for the third part, rho of v by rho of z is equal to, so the value of, and just let me write the equation for v again. It is 100 rho cos of phi divided by z square plus 1. So now we have to take the partial derivative with respect to z. So I can say the elements that are not needed is 100 rho cos of phi, and then you take partial derivative with respect to 1 by z square plus 1. Okay, so here we can apply the inner and outer rule, or we can do one more thing. We keep 100 rho cos of phi as it is, and I can say it is z square plus 1 minus 1, and now I can apply the equation. So this comes out to be, if I take the partial derivative of this one with respect to z, so the rule is basically, I'll write the rule over here. If I can take the outer value of f of u, so this outer value, or let me use another color for this. So this is my outer value, the minus 1. So this is basically my f of u, so I can replace the equation of u of minus 1. And now if I take the derivative of this, it is going to be minus 1 u of minus 2. This is what I am getting. And similarly I can take the inner chain as well, so let me use another color for that. Now this is my inner chain, so I can say this is let's say g of z. I'm replacing this, so this is going to be z square plus 1. If you differentiate it with respect to z, you will get 2 of z. So this is the answer I am getting, which means when I incorporate both of these elements into my solution, so my solution comes out to be 100 rho cos of phi, and then I'll get the answer of minus z square plus 1 power minus 2, just incorporate everything, multiply it with 2 of z. So this is the partial derivative along z. So finally my answer comes out to be minus 200, you multiply everything, rho cos of phi divided by z square plus 1, you bring z square back. So this is your partial derivative of EV along z. So this is the solution to the third partial derivative. This was solution to the second partial derivative, and the first partial derivative is over here. So now incorporate everything into equation number 1. So equation number 1 is that electric field intensity that we want to find is the negative of the gradient of V, which comes out to be, so if I incorporate everything, it comes out to be value of 100 rho cos of phi divided by z square plus 1 along a of rho, then you have minus 100 sine of phi divided by z square plus 1 along a of phi, and then you take the final value of minus 200 rho cos of phi. I think I missed over, this is 2 of z, so this is z as well, sorry about that. So this is z divided by z square plus 1 whole square along a of z. So this is the voltage that we figured out, or the partial derivative we have figured out. Now we need to solve this at p. So in order to get this at p, we just incorporate the value of p, that is basically 2 for z, 60 for pi, and 3 for rho. So at p, so this means if I incorporate everything over here, so this is 100 and rho is 3, and you have, okay, let me check if I'm missing everything. The first answer is not having rho, it is 100 cos phi, so this is wrong, there is no rho over here, it is 100 cos phi, sorry about that. So it is 100 and cos of phi, so you just add the value, so this is cos of 60 degree divided by 2 square plus 1 along a of rho, then you have minus 100 sine of phi is having a value of 60 divided by 2 square plus 1 along a of z, and then you have minus 200, rho is 3, cos of 60 degrees, z is 2 divided by 2 square plus 1 whole square along a of z. So Once you solve this, you get a value of 10 along A row minus 17.32 along A5 and minus 24 along A of Z. And since this is a negative value, so we can just replace it with electric field intensity is going to be negative 10 plus 17 and plus 24 volts per meter. So this is the answer that I am getting. Let us see if it is not correct or wrong. So it comes out to be negative 10 plus 17 plus 24, and this is what we are getting, negative 10 plus 17. So this is the solution to the second part. So now let's come to the solution to the third part. Solution to the third part is we need to find the magnitude of C, and then in the fourth part we need to find dV by dN. So in the solution to the third part, so now let me check my pointer so it becomes easy. So solution to the third part. Now in the third part we need to find E of P, which is basically the E magnitude. So the maximum value of electric field we found is this one, so we just take its absolute to get the solution at point P. So this is important that the solution is at point P. So if you take the magnitude of this equation, you should get, so I'll just incorporate the value, minus 10 square plus 17.32 whole square and plus 24 whole square magnitude. It comes out to be 31.2 volts per meter. So this is the solution to the third part. Now what is the solution to the fourth part? In the fourth part we need to find dV by dN. So this is what we need to find, dV by dN. Okay, so in our proof in this lecture we have already seen that we replaced dl, we had seen that we had replaced the voltage along a distance into dV by dN along a unit vector. This is what we had done, and we are already familiar that the value of this dV by dN is when we have a maximum value of dV along AL. So we can utilize this because this portion over here basically gives us electric field intensity. So this means that dV by dN, if we do the solution, then comes out to be dV by dL. We get the maximum value. This gives us the magnitude of E. So since magnitude of E is already proven in the previous part, this solution comes out to be 31.2, and this will be volts per meter. So this is the answer for dV by dN. So again the proof is important because the variations of voltage or the potential per unit length is varying, and this is the solution to the D part. Now what is the solution to the E part? So in the E part we have been asked to find the direction of AN, which is the normal vector. So again the direction of AN is straightforward. We can go back to our dV by dN equation because we already know that the maximum value of E comes out to be dV by dL when we have max, and this is also equal to dV by dL max but with a negative sign along A of n. So A of n from this comes out to be negative 31.2, and that is the answer. So that's easy. Now what's the final part? So in the final part we have been asked to find the volume charge density. Okay, so in order to find volume charge density, we don't need to go to the electric fields equations that we saw in the second chapter or the potential equations that we saw in this chapter. That is also acceptable, but we want the simplest term. So the simplest method is that we already know that the Maxwell's first equation is helpful in this scenario. We know that divergence of D is equal to rho V. So this is the first Maxwell's equation which we saw in the third chapter. So with this we know that D can be figured out if we take epsilon of E, and E is already given to us. So we have all the data. So what we can do is we can just use this equation to find D because E is known to us, and then incorporate it into divergence of D. So the answer, I leave it for you as an exercise, comes out to be minus 234 picocoulomb per meter cube. So this is the value of rho v that we have figured out, keeping in mind that this is the cylindrical coordinate system. So please take this question, or this part rather, as a home problem and solve it where the answer is given to you. So that concludes our today's session.